Hello, this podcast is on mechanical equilibrium, and in this short podcast we're going to understand what is mechanical equilibrium and what role do balanced forces play in mechanical equilibrium, and finally we're going to learn how to quantitatively analyze force diagrams for objects that are in mechanical equilibrium. First, what is it? An object is in mechanical equilibrium when forces acting on it are balanced in both the vertical and horizontal dimensions. Its acceleration is zero. As a result, its motion is motionless, which is called static equilibrium, or constant velocity, which is called dynamic equilibrium. Let's look at a process for quantitatively analyzing force diagrams when the object's in mechanical equilibrium. Here we have a plane, a jet plane. It's a 10,000 kilogram plane, so the mass is 10,000 kilograms. It's flying at a constant altitude and constant velocity. Its engines exert 5,000 newtons of force on it. So let's look at a process for analyzing this. First, we want to draw the force diagram and, if necessary, break forces into their x and y components. So here's the force diagram. We have gravity pulling the plane down towards the center of the earth. We have the lift force pushing up on the plane. We have the engine thrust pushing the plane to the right. And we have the drag force of the air pushing the plane to the left. We know these forces are balanced because the problem says the plane flies at a constant altitude. That's telling us it's not moving up or down, and it's at a constant velocity. That means it's not speeding up or slowing down as it moves to the right. Our next step then is, if we know the mass, use the weight equation to determine the strength of the gravity force. So we do know the mass, and here we go ahead and plug in the mass into the equation. We find out that the strength of the gravity force is 98,000 newtons, and of course it's in the down direction, which is the negative direction. Next, we want to label other known forces. Well, if we go back to the problem, they told us that this thrust force is 5,000 newtons. So we go ahead and label that. Next, we have to ask ourselves, is the object in mechanical equilibrium? We have to go to the problem description to look at that, and the problem says it's flying at constant altitude, so that means the y forces are balanced, and it's flying at a constant velocity. That means the horizontal forces are balanced. So yes, this object is in mechanical equilibrium. So then we need to calculate the strength of the remaining vertical forces so the forces balance. Well, if we look at the vertical forces, we only have two of them. We know that the force of gravity is negative 98,000 newtons. That means that the lift force has to be 98,000 newtons in the positive direction. And lastly, we need to calculate the strength of the remaining horizontal forces so the forces balance. We know the thrust force is 5,000 newtons, and the only other force to the left is the drag force, so we know it needs to be 5,000 newtons strong, but in the negative direction. So this is how we use this step-by-step process to determine the strength of all the forces when an object's in mechanical equilibrium. Let's look at another problem that's a little more involved. Here we have a dad pulling his son in a wagon. Notice that the angle of his pull force is 30 degrees above the positive x-axis. So let's go ahead and go through this process we learned in the previous slide. First, we need to draw the force diagram. Now notice Dad's tension force is not on the x or y axis. That means we need to break it into its x component and its y component, which we've done here. We know that Dad's pulling his son at constant velocity, so that's telling us that these two horizontal forces are balanced, so we're going to put equality marks on them. Let's move on. We're given the mass, so we can calculate the strength of the gravity force, which is 588 newtons in the negative direction. Let's look at the known forces. Well, in the problem, it told us that Dad was pulling the wagon with 300 newtons of force. Next, we need to calculate the strength of the x and y components of the tension force. And let's start with the horizontal component. We take the strength of the total force, which is 300 newtons, times the cosine of the directional angle, 30 degrees, and that gives us a horizontal component of the tension force of 261 newtons in the rightward direction. Next, we look at our vertical component, and again we take the strength of the total vector, 300 newtons, times the sine of its direction, which is 30 degrees, and that gives us an upward force of 150 newtons. As a final step, we need to find the strength of the normal force and the strength of the friction force, realizing that our horizontal forces and vertical forces must be balanced. Let's look at the vertical forces first. So we know that the gravity force is 588 newtons in the negative direction. That means that our normal force plus the y component of our tension force have to equal 588 newtons in the positive direction. So if we take the 588 newtons and subtract from it the strength of the y component of the tension force, that leaves us with 438 newtons that the normal force has to push up on the wagon in order to balance the gravity force. Moving on to the horizontal dimension, we only have one force leftward and one force rightward, so the friction force has to be equal in strength, 261 newtons, and in the opposite direction of our horizontal component of the tension force. Let's move on and look at a more difficult problem. In this problem, the car is parked on the hill. This will require us to rotate the axes to do the force diagram. So it's a 3,000 kilogram car, and it's parked on a hill that has a slope of 30 degrees. So here's our force diagram. We rotated our x and y axes. Gravity, of course, is going straight down, and we can break this into its y component and x component because the gravity force is not on the x or y axis. We have the hill pushing up on the car perpendicular to its surface, so that's on the y axis, and we have the hill exerting a friction force on the car, and that's in the negative direction. The problem said the car is parked, so we know the car is motionless, perpendicular to the hill and parallel to the hill. Therefore, the forces are balanced along the y-axis and the x-axis. Our next step is to use the weight equation to calculate the strength of gravity acting on the car. The force of gravity is equal to 9.8 newtons per kilogram times the mass of the car, 3,000 kilograms, and that gives us a magnitude of 29,400 newtons. Notice I'm not putting a minus sign here because I can't use that for the direction of gravity because gravity's not lying on the y-axis. So next we need to find our directional angle for gravity, and for that we'll go ahead and start counting counterclockwise from the positive x-axis, 90 degrees, 180 degrees, 270 degrees. I'm still not there, but I know that that extra amount is going to be the slope of my hill, or 30 degrees. So 270 degrees plus the slope of 30 degrees gives me my directional angle for gravity, which is 300 degrees. Now I can go ahead and calculate the horizontal and vertical components of the gravity force. And horizontally, I'll take the strength of the gravity force, 29,400 newtons, times the cosine of the directional angle, 300 degrees, and that will give me a force of 14,700 newtons in the positive direction on the x-axis. Moving down to the y-axis, I take the 29,400 Newton strength of the gravity force, multiply it by the sine of the directional angle, 300 degrees, and that gives me a y component strength of 25,461 newtons in the downward direction. Once we know the components of the gravity force, we can move on and find the strength of the normal force and the friction force. The normal force has to balance the y component of the gravity force, so it'll be 25,461 newtons in the positive direction, and the friction force needs to balance the horizontal component or x component of the gravity force, so the friction force is 14,700 newtons in the negative direction. Well, this wraps up our lesson on mechanical equilibrium. Let's review what we've learned. First, an object is in mechanical equilibrium when the forces are balanced in both the vertical and horizontal dimensions. Have to be balanced in both dimensions. An object's motion, when it's in mechanical equilibrium, is either at rest or moving with constant velocity. If the object's at rest, that condition is called static mechanical equilibrium. If the object is moving at constant velocity, that condition is called dynamic mechanical equilibrium. In both cases, the forces need to be balanced and the acceleration is zero. Finally, we can use the concept of mechanical equilibrium to determine the strengths of the forces acting on an object. This brings an end to our podcast. I hope it helped you, and have a good day.